Good afternoon, everybody, and welcome to what is the second of Imperial Science Breaks events. Thank you very much to everyone for joining us. So to introduce myself, I'm going to be your chairperson for the day. My name is Adam Masters and I'm a space scientist in Imperial's Department of Physics. So today's event is called After Cassini, Probing the Icy Moons of Jupiter with JUICE, and it will be given by Professor Michele Dougherty. So Professor Dougherty's topic is planetary science and solar system exploration. She's done a lot of different work, particularly on the Jupiter system and the Saturn system, which includes the various moons of those two giant planets. Her work has focused very much on the interiors of those planets and how they generate strong magnetic fields, as well as what happens when those fields extend out into space. And also a major thing she's worked on is trying to understand if there were oceans of water underneath the icy surfaces of some of the many moons of Jupiter and Saturn. Now, I'm not going to say any more about Professor Dougherty's topic because she's going to talk about her topic at length in a few minutes' time, but I want to give a brief introduction to Professor Dougherty herself. So before joining Imperial, Professor Dougherty obtained her degree and PhD from the University of Natal in South Africa, before she then moved to Germany, where she worked as a research space scientist. After joining Imperial, she then rose rapidly to a position that she currently holds, which is a professor of space physics, and she's now actually the head of our entire Department of Physics itself. Now, Professor Dougherty's won numerous awards, and I don't really have enough time to go through all of them. I just want to highlight a few really important and relatively recent ones. She's been made a Fellow of the Royal Society. She was awarded the Royal Astronomical Society's Gold Medal. And in the 2018 New Year's Honours List, she was awarded a CBE. Now, all of these awards are for her major contributions to both national and international space science and planetary science. I want to just finish this introduction to Professor Dougherty herself with more of a personal perspective. So I'm in the same field as Professor Dougherty and have worked with her for quite a few years. And I think that she's got a rare talent which actually goes beyond her expertise in her field. Clearly from these awards I've just described, she's a world expert in her topic, but she has a rare ability to grasp the science of other disciplines, and planetary science has lots of different diverse disciplines. And Professor Dougherty's understanding of all these different topics is why she has such a good grasp of the big picture. And I think that's actually a major reason for her remarkable success leading international space mission projects like those she's going to talk to us about today. Now, these projects are projects that lead to huge advances in what we know about the solar system, and also they support whole cohorts, almost generations of young planetary scientists coming through obtaining their PhDs. So I was one of those young planetary scientists once, maybe not so anymore, not so young now, but it's for that reason that I'm very pleased to be able to give this introduction. And I hope that Professor Dougherty is not too embarrassed by it. Okay, so finally, just before handing over to Professor Dougherty to give her presentation, I want to cover a couple of housekeeping items. Please feel free to submit questions for Professor Dougherty at any time you like. You can do that using the Q&A section at the side of your screen. So this event is being recorded, and if you do not want your name to be read out with your question, then please submit your question anonymously. That's absolutely fine. Now, if you like a question someone else has asked, maybe it's a question you were planning to ask yourself, then in the Q&A section, please just like the question that you were planning to ask so that I get an idea of the most popular questions, and during the Q&A, I'll make sure that we ask those first. Following Professor Dougherty's talk, there will be a very short break of a couple of minutes, and at that time you can still submit final questions before the Q&A kicks off. Okay, so without any further ado, I'm going to hand over to Professor Michele Dougherty to talk about the world after Cassini.
Thank you very much, Adam. Thank you very much, Adam. I don't know if I'm live. Adam, can you give me a thumbs up if you can hear me okay? Great, because I can't see myself, so I wasn't sure if I was now going live. So hello, everybody, and thank you very much to Adam for the very nice introduction. I've known Adam for a long time. When he began his PhD with me, he had a lot more hair than he has now. And he blames me for that, and I'm not going to get into that now. So what I'd like to talk to you about today is the results that we were able to gain from the end of mission from Cassini, and how those really informed what it is that we are now going to be doing for the Jupyter mission called JUICE. And I always like to start these talks with a view of Saturn, which you can see on your screens here. And that's really the entire Saturn system. You can see Saturn itself. You can see all of the visible rings here. I hope you can see my mouse moving. You can also see a new, well, not a new ring, but a ring called the E ring, a diffuse ring. And if you look really closely, you can see some outgassing in that ring. And that outgassing is coming from the small moon Enceladus, which is one of the things that my team discovered at Saturn, was that there is this very small moon which is outgassing water vapor, and that has been a real focus for research for life in the solar system going forward. And then last but not least, before I move slides, let me just point out the Earth is where my mouse is. And it always makes the hair on my arm stand up on end when I can see that, because there was the spacecraft out at Saturn looking back at the Earth and being able to take an image of us. So what I'd like to do is, some of you might have seen my Schrödinger lecture where I described in quite a lot of detail the Cassini mission and its science. But what I wanted to briefly touch on today is the magnetometer observations and what we learned from the end of mission phase. And this view here essentially shows you the spacecraft as it was diving between the rings of Saturn and the upper atmosphere. And the observations that we made at that time have given us an understanding of the internal structure of Saturn that we really didn't expect to be able to get. One of the things that we use magnetic field observations to do is to try and get an understanding of the internal structure of the body that we fly past. So if you have a look at the picture on the top left here, what my instrument does is it's able to measure these blue field lines here. And these are the field lines where, if, for example, you were standing on the surface of the Earth and you had a compass, the actual needle on the compass would point to the north pole of the magnetic field. And you have something very similar at Saturn. You have these blue field lines that you can measure if you fly close by. What that allows you to do is not only measure the strength of the magnetic field, but also, depending on what the field lines look like, you can actually get an understanding of what's going on in the interior of the planet itself. What we think is happening, if we look on the bottom right, is we think that there are two different processes that are taking place. There's the rotation of the planet, which is allowing a bubbling motion to take place. But in addition to that, there's a convective motion. It's a little bit like a pot of porridge bubbling on the stove. You've got the heat being given off in the interior, and those two different processes go towards what is known as the planetary dynamo. And magnetic fields that we measure at the Earth and at other planets are generated by this planetary dynamo action that takes place inside. What you have is you have electrical currents that flow, and those currents generate a magnetic field, which is what we're able to measure. Now, one of the real surprises about Saturn, and we were not able to resolve it in the first 12 years that we were in orbit around Saturn, is that the rotation axis, so the axis that you can see here, about which the planet rotates every day, and the magnetic axis, so the axis about which these field lines lie. Usually for dynamo action to take place, you need there to be a tilt between those two axes. On the Earth, it's at about 22 degrees. At Jupiter, it's about 10 degrees. At Saturn, we were not able to measure a tilt. And that means we don't understand how the planetary dynamo works, because you need a tilt for that to be able to work. So that's effectively why we were able to persuade the Cassini project to take us so close at the end of the mission and get really close to the planet and see whether we could measure that tilt. And I'm going to show you 2 slides which show you some of the end of the mission data. And what the data tells us is there is not a tilt. What it tells us, in fact, is that we think we have differential rotation in the deep interior. So the image of Saturn that you can see to the left there, what that actually tells us is if we subtract the higher order moments of the field away from the data, what we see is these zonal jets, these different colored zonal jets, which are very similar to what we see in the atmosphere. And what that's telling us is the magnetic field is actually consisting of 2 separate dynamos, a very deep dynamo right in the middle of the interior, and then a much shallower dynamo, which is what we can see out here. And this is the first planet where we have been able to resolve these 2 different dynamos. And it's really turned dynamo theory on its head, and it's got theorists trying to understand how they can actually form. And so this is a plot that came from the end of mission science paper that we published. And what I want you to focus on is, again, the planet itself. You can see the field lines that we measured on the outside of the planet, but within the planet itself, there is a deep dynamo, which is what we have at the Earth, and a Jupiter. There is then a stable layer above that, but then there is the secondary dynamo, which you can see with these little field lines with lines on them. And it's this secondary dynamo which is essentially masking the effect of the deep interior. And so Saturn is unique in this instance, and we still don't quite understand why we've made the observations and we found that the interior of Saturn is made up in such a strange way compared to the other large planets in the solar system. So moving on to one of the discoveries that I mentioned that we had made, and this was this outgassing of water vapor from Enceladus. So you can see in the top right of the image here, this shows you a view of this outgassing of water vapor. And this we were able to see on a flyby of Enceladus quite early on in the mission from our data. We persuaded the project to fly us much closer. And in fact, when we flew through this plume that you can see here, these are some of the constituents that we were able to measure. And so the really interesting constituents we measured was water vapor. And we have been able to decipher that there's actually liquid water underneath the surface of Enceladus. We also measured simple organic material and complex organic material as well. And because we have liquid water at these great distances from the sun, the implication is there's a heat source as well. And so that's why Enceladus has become so interesting to planetary scientists, because it has 3 of the 4 ingredients you need for life to potentially be able to form. It's got a heat source, it's got liquid water, and it's got organic material. What we don't know is how stable these 3 ingredients are, whether they're stable enough over a long enough period of time that something can actually happen and life of some kind can form. And so it was really following the Cassini observations of Enceladus and the NASA Galileo observations of the moons of Jupiter that allowed us to persuade the European Space Agency that we should fly the mission JUICE, which is going to go to Jupiter. And the reason that we were able to persuade them to do this is as follows. And I think this is, for me, the real discovery that we've made in planetary science in the last 30 years. And that is that you don't need to be close to the sun for liquid water to be able to form. So before I say too much more, let's actually take a step back and look at this figure that you can see here. What this is showing you is that it's now accepted that there are 2 habitable domains in every stellar system. There's a very narrow one, quite close to the parent star, where you expect to find liquid water on the surface, for example, as we have on the Earth. But there is this much bigger domain beyond what is called the snow line, which is this yellow dashed line that you can see here, where water is very abundant, but it's not found on the surface. It's too cold out there to be found on the surface. And so what you do is you're able to find it in these deep reservoirs or oceans underneath the surface. And the Jupiter system and the Saturn system are in this domain, and you can see them here. At Saturn, we have Enceladus, and we've also got Titan shown on the right here. And at Jupiter, we have both Ganymede and Europa that are shown here. And this is where you have these deep habitats, potential habitats, where you have liquid water. And so what we're going to do with JUICE, and I'm going to show you some slides a bit later that show you this, is we're going to explore 3 of the moons of Jupiter. We're going to explore Ganymede. We're in fact going to go into orbit around Ganymede. And we're also going to have many flybys past Callisto and past Europa as well. So before I talk a little bit about those moons, let me just give you an understanding about what understanding these 3 moons better will be able to do for us as far as understanding the variety of planetary bodies that we have in our solar system, but also potentially outside of our solar system too. So what you have in this schematic here is along the bottom of the picture, you've got 5 different families of planets. You've got Mercury-like on the left, going through Earth-like, water worlds, something between water worlds, and then the gas giants. And what we have going from left to right is it's the amount of silicates followed by water, and then finally hydrogen and helium that are increasing as you go to the right. Now, by the time we get to Jupiter in 2030, we don't know how many thousands of planets might have been discovered outside of our solar system. But what we do know is only 2 of these families will be properly characterized by then. The Mercury-type objects from the 2 spacecraft missions, Messenger and Bepi-Colombo, and the Earth-like objects, which of course we know a lot about because we are on one. So what JUICE is going to do is, by thoroughly exploring Ganymede, which is a water world, we're going to really be able to characterize an entire class of planets. And so it was the search for habitable environments and being able to understand better a 3rd class of planets that allowed us to persuade the European Space Agency that we should go to Jupiter and its moons. And before I show you what we're going to do with JUICE, let me just take a step back in time. And this is our understanding of the internal structure of 4 of the moons of Jupiter. And this is following the NASA Galileo spacecraft, which orbited around the Jupiter system in the late 90s. We've got Io in the top left, which is a volcanic moon. It's spewing out a lot of sulfur dioxide. We've got Europa in the top right, where we have an ice shelf with a liquid water ocean just underneath the surface. We have Ganymede in the bottom left, which is a very large moon, one of the largest moons in the solar system, and in fact the only moon that has its own internal planetary dynamo. So if you're able to stand on the surface of Ganymede and you had a compass, it would point to the North Pole of the dynamo. But in addition to that, you can see this very clear liquid layer, which is one of the things we want to try and study by going into orbit around Ganymede. And then last but not least, on the right-hand side, we've got Callisto, where again, we think we might have liquid water under the surface. And we want to try and understand why there isn't a solid core. So that was our understanding of the 4 moons of Jupiter. And that's what we want to try and further. So what we're going to do is we're going to fly a spacecraft called JUICE. Here is an artist impression of what the spacecraft looks like. It's going to be the first time that solar panels are used on a large planetary mission. The Jupiter system is as far as we can go and use solar power. If we went to Saturn and tried to use solar power, the solar power isn't strong enough to be able to drive the spacecraft and its instruments. And what you can see here is Jupiter in the background, and you can see Ganymede. And so what we're going to do is we're going to spend 3 years in the Jupiter system. And in the last 6 months of the mission, we're going to go into orbit around Ganymede. And we're going to make measurements of the magnetic field of Ganymede, which will allow us to get a better understanding of the internal structure. So this is, there are two different science areas that my team was going to focus on. And the first one is really the most difficult one. And to be frank, I'm losing sleep over whether we're going to be able to resolve the very small signatures that we need. So what we're going to try and do is we're going to try and measure currents, electrical currents that are flowing in the liquid water ocean. And these are induced by the magnetic field of Jupiter. And these electrical currents generate a magnetic field, and it's that magnetic field that we're going to try and measure. But, and I've described this to colleagues as what we're trying to do is we're trying to find about 5 different needles in a haystack, and those needles are changing shape and color all the time. And so when I wake up in the early hours and I can't get back to sleep, this is what I worry about, is whether we can build an instrument that is sensitive enough to be able to make these kind of measurements. What we want to be able to try and do, if you look at the top right here, is we want to be able to try and work out how deep the ocean is, what its salt content is, and whether it actually covers or is underneath the entire surface of Ganymede. Is it a global ocean or is it a local ocean? At Europa, for example, we will have 2 flybys of Europa. We're almost certain it's a global ocean based on the observations from the Galileo spacecraft. At Ganymede, we think that's the case, but we need to be able to try and understand that best and make sure. And of course, we're not going to be able to understand these kind of observations on our own. We're going to put together data from all of the other instruments on board the spacecraft. And as Adam mentioned in his introduction, for me, this is the real strength of the large planetary missions that we are involved in, is that we collaborate with all the other teams. We put together data from all the other instruments so that we can really best understand what's going on. The second area that we're focusing on is really understanding the entire environment around Jupiter. We're going to understand the aurora, the northern and southern lights that we have on the Earth, and we have them on Jupiter as well. And they actually allow us to get an understanding about how the moons are linked by the magnetic field of Jupiter to Jupiter itself. You can actually see in the bottom left here, you can actually see a little footprint, which is actually generated by the connection between Ganymede and Jupiter. And we can actually see how that evolves over time. In addition, Ganymede has aurora of its own. And so when we go into orbit around Ganymede, as my cursor is showing here, we're going to really be able to better understand the whole of the Ganymede system. So keeping an eye on the time, I have one final slide, and that's really linked to how stressful it's been trying to build an instrument which we will fly on the JUICE spacecraft while the lab has been closed. So Imperial College went into lockdown in the middle of March. We were given 48 hours notice that we had to close all of our labs down. And so for about 6 weeks, we did nothing. We essentially put the instrument into cold storage, and we weren't able to do anything as far as building the instrument itself. We were able to go back and have a look at a lot of test data, help us understand the instrument better. But we were really fortunate in that we were able to allow our engineers some access to the lab over time. So the last 6 weeks or so, we've had a couple of engineers being able to go into the lab. What we haven't been able to do, though, is to fly to the European Space Agency and do any tests on the instrument. So what we've done is we've done these remotely. We've been on WebEx and Zoom calls where we've been watching what the engineers at the European Space Agency have been doing to carry out tests on the instrument. And so let me point out what we're looking at here. So top left, we have the electronics box of the instrument, this black box that you've got here. And then we've got the 3 different sensors that make up our instrument. So this is the outboard sensor, which we're building at Imperial College. This is the inboard sensor, which is about 1.5 meters away metre and a half away from the outboard sensor. That's built by our COIs, our colleagues in Germany. And then on the right here, we have a new sensor, which hasn't flown in space before, which measures not the three vectors of the magnetic field, but the magnitude of the field. And this scalar sensor is right on the end of the boom that we place our instrument on, and that's being built in Austria. And this was the entire instrument just before it went into the vacuum chamber, where we were able to test the instruments in the vacuum that they're going to see in outer space, but also the range of temperatures that they were going to see. Our instrument needs to be able to operate safely from a range of minus 160 degrees Celsius up to 40 degrees Celsius. So we need to carefully be able to test that the instrument works. Bottom left, we have the engineering, we have the electronics box on a shake table. And so what happens is that we shake the table, we vibrate the instrument to make sure that it will survive the rigors of launch. And then on the right here, again, we have the electronics box, and we have an engineer standing here with a large stick that he's about to drop. And when he drops that stick very close to the instrument, it gives it a shock. And this is also to make sure that the instrument would survive. Now, when I've been talking about the instrument here, this is just before the flight instrument. We build lots of different models. This is known as the qualifying model. We put the qualifying model through all these different tests to make sure that our design works. And in fact, it does. It survived all the tests, and we now, a couple of days ago, actually started building the flight instrument in the lab a couple of floors below me. And I'll stop there, Adam, and give us some time to have a break, and then we can take some questions.
Thank you very much, Michelle, for a very interesting presentation. And I can see there's lots of questions in the Q&A, and some of them have been liked by quite a few people, so lots to talk about. We're going to take a 2-minute break, so please come back in 2 minutes, and this is your final chance to post questions to the Q&A. Thank you very much. See you in a couple of minutes. Okay, welcome back, everybody. As I said just before we took that very brief couple of minute break, thank you very much to everybody who had submitted questions on the Q&A. There's quite a few, and there's a few that have been liked by quite a lot of people. So before I start repeating these questions and allow Michelle of course, to answer them, I want to apologize in case I mispronounce anyone's name if you have put your name in the question. So apologies in advance if I do that. So the first one I'm going to go with, which is the most liked, is from Rohin Nair. And the question is, if we could, where would you send a manned mission to in the future? Europa or Titan, and why?
Interesting. Where would I prefer to go? I think it would need to be Europa, just because I think it's easier to get below the surface at Europa. You know, one of the things that when we say we're searching for life or for potential habitability, what we need to do is okay, if the ingredients are there, that's fine, but we need to be able to get underneath the surface and see what's underneath the surface. And at Europa, we think the ice crust is very thin. And so that would be my first choice, would be Europa over Titan, although some of my Titan colleagues probably wouldn't like that answer.
Thank you, Michelle. Okay, so we'll move on to the next one. Almost as many likes for this one. This is from Junaid Saeed, and the question is, how far in number of years are we away from a manned mission to one of the celestial bodies? So I imagine this means not the Earth's moon, but I guess this includes Mars in the question where they refer to celestial bodies. So over to you, Michelle.
I would say the next 20 to 30 years. I think if you had asked me about the outer solar system, I would have said beyond my lifetime. But I think we have everything in place that is necessary, except the ability to be able to survive, for example, at Mars without having to take everything with us. You know, being able to generate water, being able to generate oxygen. If you're going to go and live on another planet, you need to be able to generate that yourself and not have to take it with you. So I would say 30 years. Whether I'll be around to see it I'm not sure.
Yeah, I'm not sure I'll be around either, Michelle. Okay, so we'll move on to the next one. This is by Firat Guda. And the question is, what is preventing us from dropping small probes on the surface of Ganymede now that we will have an orbiting spacecraft? Is it that propulsive landing is required, or the surface is not too stable, or just simply the cost?
I think it's the cost. And it raises I think an even more critical point, and that is, for me, if you're going to drop things on the surface, whether it's Ganymede as you've asked, or whether it's sending a lander to Europa, which some people want to do, I don't think we should be doing that until we know where on the surface we want to go. And so a mission like JUICE, where we will go into orbit around Ganymede, that is going to allow us to map the surface in a huge amount of detail and get an understanding about the thickness of the ice crust. And once we know that, then we should follow up with sending probes onto the surface so we can pinpoint exactly where it is that we want to go. So I think at this stage it's the cost, but I think it's good that we have a reason not to do it just yet. Let's do things in the right stages.
Okay, great. So, sorry, Michelle, more questions to be fired at you.
That's okay.
This next one is from Charmilla, and the question is, how does a moon's magnetosphere come into being in the first place?
A moon's magnetosphere will arise if the moon has a magnetic field. And so what happens, Ganymede has its own internal planetary dynamo. And that means that what the magnetic field does, it effectively protects the moon from the effects of the environment around it. And so what's really interesting about Ganymede is you have a moon with a magnetic field, which is embedded in the magnetic field of Jupiter, and then Jupiter is embedded in the magnetic field of the solar wind. So it's almost a little bit like those Russian dolls that you get, where you have all of these little things inside of each other. And so for me, that's why Ganymede is so interesting, is for someone who builds magnetometers, it's the ideal place in the solar system to go. You have all these different magnetic fields that you're trying to understand. And we think Ganymede's the only moon in our solar system that has its own internal dynamo.
Great. So the next question concerns Enceladus. So this is, I believe Steve Jackson asked this question, and it is, revisiting Enceladus to search for life seems to be almost inevitable. Discovering life there would have profound implications. My question is, if a future mission could sample the plumes with updated equipment specifically designed to find signs of life, would that be able to determine definitively if life is present there?
I think we need to get under the surface to be able to definitively say if there is bacteria of some kind there. I think we need to go underneath the surface. I think the instruments that we had on Cassini were pretty good at almost sniffing what was in the plume and measuring what was in the plume. I'm trying to think if there is an instrument that we could fly through the plume with which could definitively say there is bacteria. I can't think of anything. Is it Steve you said who had asked this question, Adam?
That's right, Steve Jackson.
Yeah, Steve, I would have to think about that. I think for us to be able to definitively find life, we would really need to get underneath the surface. Partly because you don't know how things are going to evolve as they go under the extreme pressure they will have to go under if they're in liquid water, and then they get outgassed under extreme pressure and become water vapor. So if there is bacteria, that will probably be changed in that process. So I would need to think about it, but I think I would prefer, if someone said to me, you've got all the money in the world, take what you need to do to go to Enceladus, I'd say I need to get underneath the surface, please.
Okay. So the next question, I think Michelle, you might have already answered this question when you answered a previous question.
Okay.
I'm going to read it out anyway, and we can double check. So it's an anonymous question. Do the icy moons of Jupiter interact with the magnetosphere of Jupiter? And if so, what would the dynamics be like and its effect on the possibility of life on the moons?
Yeah, I sort of alluded to that, but that's a very interesting question. And it actually takes us to the question of why these moons of Jupiter have got liquid water underneath their surfaces. Why have they still got heat in the interior? You know, the size of the moons, we would have expected that they would have long since cooled down from when they first formed. They shouldn't have heat in the interior. And it's the orbital resonances of these moons. It's the way they orbit around Jupiter. So as they orbit around Jupiter, they're not quite in a complete circular orbit. And so in some parts of the orbit, they're closer to Jupiter than others, and the tidal forces are different. But also, Io, Europa, and Ganymede are in an orbital resonance, where every time every time Ganymede orbits around Jupiter once, Europa orbits twice, and Io orbits 3 times. And those resonances all play a role in why all 3 of those moons have still got internal heat sources. So the orbital resonances are important. Aurora are formed. I showed you the aurora on some of the images. That's one way in which the moons are in connection with Jupiter. I'm trying to think if there's another way. I think those are the 2 most important parts to it, yeah.
Okay, thanks, Michelle. The next question is a classic question that we get asked all the time, of course. It's a classic "so what" question.
Okay.
And I promise this doesn't come from me. The person asking the question is called Adam, but it's not me.
Okay. Hello, Adam number 2.
Adam, so the question is, why is it important to do this at all? What benefit is it to humankind?
I see us as explorers. I think humankind is part of their DNA is they want to explore. Some of the early explorers worked out that the Earth was round and not flat, and so that's what I see. We are helping explore our solar system. We are helping understand how life formed. We're helping getting a better understanding about what implications that might have as to how the Earth evolves over time. I mean, and I didn't have time to talk about this, but one of the reasons we were so interested in Saturn's moon Titan is that we think the atmosphere of Titan is very similar to what the Earth's atmosphere is like when it first formed. And so that gives us an understanding about how the Earth and its atmosphere evolved. So for me, it's getting an understanding about where else in the solar system and potentially outside of the solar system we have the ingredients for life to form.
Great. Your mention of Titan just now is a good lead into the next question.
Okay.
Lots and lots of different topics here. The next one, as I said, is Titan focus. So this is a question from Mark New, and the question is, what is the current scientific assessment of life on Titan? Cassini found the first signs of hydrothermal activity, making this tiny Saturn moon one of the leading locations in the search for life.
Yes, Mark, I agree. It is one of the places in the solar system where we want to focus. And that's why, in fact, there are lots of studies going on at the moment as to what kind of mission we should be sending to Titan next. I think NASA is planning a mission that has a balloon, which will fly through the atmosphere, but also will drop a probe into one of the oceans at Titan. But you know, when you talk about life on Titan, it's certainly not life as we understand it, because you have the liquid on Titan is not water, it's liquid ethane and liquid methane. But you're right about the hydrothermal vents. There's the heat source, organic material. And so, yes, it's certainly one of the places. You know, in the outer solar system, I think there are four places. There's Europa and Ganymede, and then there's Titan and Enceladus. And those are the 4 moons that I would want to focus on if I could study them all at the same time.
Great. So the next question is from Kanishka Deepak. And the question is, how habitable are the moons of Jupiter? So I think this is along the theme of what the response you just gave, Michelle. So the question, how habitable are the moons of Jupiter? And a secondary question in there is, what is the density of air on Jupiter and its moons? So I think that's referring to the density of the atmosphere, so on the surface and surface habitability. I
don't know the answer to the density question off the top of my head, I'm afraid. I would need to go and look. I'd need to go and look that up. As far as how habitable the moons are, it would be very difficult for bacteria even to survive on the surfaces of the moons of Jupiter, because the environment around Jupiter is very radiation high. And so if we are going to have a chance of finding potential habitability at the moons of Jupiter, I think it's going to have to be below the surface, where the bacteria, for example, is protected from the radiation environment. I think if I had to choose one moon at this stage where the likelihood is highest to find the ingredients or confirm the ingredients we need, I would say it was Europa, partly because we know it has a very thin ice crust, and it will be much easier to get underneath the surface, or have water which is underneath the surface leaking out. In fact, if you have a look at some of the images of the surface of Europa, they remind me very much of what the Greenland ice shelf looks like. If you're on a plane, when we can all finally fly again, and you get on a plane and you fly from Europe or the UK to the US, and you fly over Greenland, you have a look out of the plane window, you can see bits of ice shelf coming off from the edge of the ice shelf, and that's essentially what the surface of Europa looks like. There is ice moving around on a liquid water surface, and there's bits of water coming up from underneath the surface. So I think Europa is probably the place where we will first find it, just because it's easiest to get to.
Great, thank you, Michelle. So at this point, we've still got 5 minutes. I've asked you all of the really heavily liked questions. I'm going to abuse my position as chair now and ask you one myself.
Oh, yeah, okay.
Out of interest. So the Enceladus discovery was a real surprise. That's why we call it such a big discovery. There wasn't expected to be a global ocean, and there is. Do you think there are any other moons in the solar system where there might be similar surprises in store?
Yes, and I think it's probably much further out in the solar system. I think Uranus and Neptune, the two large gas giants very close to the edge of our solar system, they have some real surprises in store for us if we're ever able to go back. I know there are some plans, or there are some discussions about potentially sending missions to Uranus or Neptune. I don't want to think about how long it will take us to get there, but I think we will probably have surprises like that as well. Yeah.
Great, thank you very much. So the next question, which is an anonymous question, is which theories for the origin of life are the most plausible on these moons?
I don't know about lots of theories. From my perspective, I think I'll refer back to the comments I made during the presentation itself, and that is that you need 4 things. Well, when I talk about life, I'm talking about life as we understand it. So, you know, you need 4 things. You need liquid water, you need organic material, you need a heat source, and then you need those first 3 things to be stable enough over a long enough period of time that something can happen. And that's where we base our understanding about how potential habitability might form. So that's what we're looking for. You know, we might be really surprised and find something that we're not expecting to find, but all we can do when we're searching for habitability is base it on our experience to date, and that's what we're doing as far as JUICE is concerned. Great.
So I think this next one might be our last question, as we're starting to run out of time.
Okay.
So this is a question from Luke, and the question is, could missions to Jupiter's moons be done by private organizations such as SpaceX or Blue Origin?
Oh, yes. They certainly can. They have the techniques, they have the experience of launching missions. I would very much hope they would talk to scientists before they did it, so they could make sure they would get an understanding about the best place to go. I think, you know, if we're going to be doing this outer planetary exploration, yes, of course we're doing it to explore, but we should also be doing it to ensure that we understand our own place in the solar system. And so, yeah, I'm sure there's room for external launchers and companies to get involved. But I would very much hope they would involve some of us scientists to choose the best place to go.
Great, thank you very much, Michelle. So I think we're now coming to the end. Maybe we've got time for one more, and then you can have a well-deserved rest.
Okay, cool.
So this one is a question I've asked myself in the past. Why does Ganymede have its ice layer below, i.e. deeper than the water layer rather than above it?
We think they're 2 different ice layers, actually. We think there's an ice layer above the water, and then there's a water layer, and then there's an ice layer below. I'm not an expert on this, but my vague understanding of it is it's to do with the different kind of internal pressures at the moon, but also the internal makeup of the moon as well. And so depending on what the pressure is at a particular depth, you're going to have either an ice layer or a liquid layer. But for Ganymede, that's what makes it a little bit more difficult to work out what the salt content of the water is because we think there's this thick ice shelf above it. And that's why the measurements we're going to make with the magnetometer on JUICE will give us some understanding, we think, of what the salt content of the water is.
Great. Thank you, Michelle. So those are all the questions we have time for. So I also want to thank everybody who's sent in questions. And thanks to you, Michelle, of course, for answering them, and apologies to anybody who asked a question and we didn't have time to get around to it. So that almost concludes this second of Imperial Science Breaks events. So I just want to end by once again thanking everybody for joining us, particularly Professor Dougherty for giving such an interesting presentation. And of course, to those of you who submitted questions, especially if they were heavily liked and we got around to asking them and allowing Professor Dougherty to respond. Thank you to all of you as well. And I'm sure we're all hoping for big success now with the JUICE mission coming up. It's very exciting, and I think we'll all watch this space. So finally, before wrapping up, I want to say, please do join us for the next of these Imperial Science Breaks events, which will be on the 6th of August. It will be at 12:30 p.m, just like today. And in that particular event, Dr. Joe Tobias will be talking about his latest research on birds. Okay, so thank you very much to everybody again. Thank you to Professor Dougherty again, and we look forward to seeing everybody soon. Bye-bye for now.